Welcome to lesson 26 on power system analysis. In this lesson, we will learn about symmetrical component analysis. If you recall, in our previous lesson, we talked about how to analyze faults on power systems. We will be continuing with that. As we have seen, most of the faults on power systems are single phase to ground faults and say line to line faults or double line to ground faults. All these faults are basically asymmetrical faults because they create an unbalance in the voltage and the currents in the three phase system. To analyze faults which are unbalanced or asymmetrical, we need help of the symmetrical component transformation. In this lesson, we will discuss about how to use the symmetrical component transformation for analyzing asymmetrical faults. So, in this lesson, first we will start with an introduction what symmetrical component transformation is. Then we will go into the sequence network for power system components, how we develop the sequence networks, and we will also talk about the relationship between phase and sequence components. The instructional objective for this lesson is that after this lesson you should be able to explain the significance of symmetrical component transformation. You should be able to develop relationship between phase and sequence current, voltage and power quantities, and you should be able to develop sequence network for load models. We will take up the other power system component models in the next lesson. Well, as I said earlier, the different kinds of faults that we have on power system are single line to ground fault, single line to ground fault, line to line fault, line to ground fault or LLG fault, and three phase to ground fault or three phase faults. Out of these types of faults, as we have indicated here, line to ground fault, line to line fault and line to ground fault are basically asymmetrical faults. As we said, these create asymmetry in the currents and voltages in the three phase of the three phase system. Except for this three phase fault, which is a symmetrical fault because the currents and voltages in all the three phases are going to be same or symmetrical, same in magnitude and with a phase displacement of 120 degrees. So, symmetrical with each other. So, to analyze faults which are asymmetrical, we need to work on three phase basis. That is, in case of symmetrical faults, we used a single phase basis of analysis because all the three phases were identical. That is, if you come to know of the current and voltages in one phase, you can always find out the currents and voltages in the other phases because they will be of equal magnitude and displaced from this phase current and voltage by 120 degrees. The situation is not same for these other type of faults, and we need to represent the three phase system in its completeness, that is, all the three phases have to be represented. Now, this creates complications because there are mutual impedances involved and we have to work with 9 quantities as such. In order to make the analysis of three phase system under unbalanced condition, we normally take help of what we call symmetrical component transformation. So, now we will see how this is done. Well, symmetrical component transformation was first introduced by C.L. Fortescue in 1918. What he suggested was we can always transform these three phase quantities into three different sets of quantities which are symmetrical. We will talk about that. How does it help? Well, symmetrical component transformation is a modeling technique for analysis and design of three-phase system. As I said earlier, the advantage of this transformation is that it decouples a balanced three-phase network into three simpler networks. Means these three simple networks are not connected to each other, they are separated from each other, and therefore, there are no mutuals involved here. For unbalanced three-phase networks, the three sequence networks are connected only at the point of unbalance, because we have in a power system most of the elements are designed to be a symmetrical three-phase system. All the generators are designed to work as a balanced three-phase system. All the motors, transformers, all are designed to work as a balanced symmetrical three-phase component. Transmission lines, as we have learned during the modeling of transmission lines, are transposed most of the time, especially for long distance lines, so that the three-phase transmission line also becomes a symmetrical three-phase system. Therefore, as we have seen, the sequence symmetrical components decouples a balanced three-phase network. So, for all these components you are going to get decoupled sequence networks. Only at the point of fault or unbalance there is going to be a coupling between these three sequence networks. Because of this particular property, it is a very powerful tool for analyzing three-phase system. It makes the analysis much more simpler to do. Another advantage is it reveals the complicated phenomena during unbalanced operation in simple terms, that is in terms of sequence currents and voltages, and we can understand the unbalanced phenomena in very simple terms of these sequence current and voltages. However, this has one disadvantage, that you need to first transform the three-phase system quantities into symmetrical component quantities. Once you have done the analysis and got the symmetrical component values for currents, voltages, power, whatever it is that we are interested in, finally, we will have to again do an inverse transformation, because finally we would be interested in finding out the currents and the voltages in the actual system. So, in terms of phase currents and voltages. So, we need to do inverse transformation to get this, that is sequence network results have to be superposed to obtain the three-phase network results. Now, what is this symmetrical component transformation? Well, as defined, it is defined as an unbalanced set of n phases can be resolved into n sets of balanced phases, which we call symmetrical components. The n phases of each set of components are equal in magnitude and angles between adjacent phases of the set are equal. That is, if we have a set of n phases which are unbalanced n phases, then we can resolve them into n sets of phases of n phases, basically n sets of n phases which are symmetrical with respect to each other. And this, if we try to use for our three-phase system, can be said as unbalanced phases for a three-phase system can be resolved into three balanced systems of phases, which we call as the positive, negative and zero sequence systems. So, what we have done is basically three-phase quantities are now being converted into three different sets of quantities which themselves are three-phase quantities. So, one would think in terms of that what we are doing is from three quantities we are going to 9 quantities, but actually this is not the case, as we will see later. What are these sequence quantities? Positive sequence components consist of 3 phases with equal magnitude and with 120-degree phase displacement from each other. This is shown here, that is, we have a phasor which is a balanced set, a symmetrical set, where we have a 3 phase quantities VA1, VB1, VC1, and these are 120-degree out of phase. This is what happens in a balanced 3 phase system. So, this positive sequence components are basically same as the balanced 3 phase components that we have. So, each that is, these phasors are displaced from each other by 120-degree and have the same phase sequence as the original phasors, that is, the phase sequence is A, B, C, A, B, C, A. So, first A is here, then it moves after 120-degree, B will be in this position, then again another 120-degree, C will be in this position, and so on. So, the phase sequence is A, B, C, A, which is the same as the original phasors phase sequence. Negative sequence components consist of 3 phasors with equal magnitudes and with 120-degree phase displacement from each other. Again here, if you see, these are 3 phasors which are equal in magnitude and have 120-degree phase displacement from each other. Again, this is a balanced set of quantities. So, balanced symmetrical set of 3 phasors we have. The only difference between the positive sequence and the negative sequence component is that the phase sequence of negative sequence component is reverse to that of the positive sequence component. That is, if we see this, the rotation of this phasor will appear to be in the reverse direction. So, phase A is here, then phase B will come here, that is, rotation will be like this. Or if we take the sequence direction in the same way, that is, rotation always as anti-clockwise rotation, then the phase sequence for this can be seen as A, then C, and then B. So, we call it as A, C, B, A phase sequence. So, basically what we are looking at is that it is a system of quantities which is symmetrical balanced set, but rotates in the reverse direction to that of the positive sequence quantities. The third sequence components are called 0 sequence components, and these consist of 3 phasors with equal magnitude and 0 phase displacement from each other. That is, they are basically of the same phase, that is, all the 3 phasors have the same phase. So, there is no phase displacement between them and the magnitude of the 3 is equal. So, these are the 3 sets that we use in symmetrical component transformation for a 3 phase system. Now, we will see how by adding these 3 sequence sets we can create any unbalanced set of 3 phasors. If you see here, we have an unbalanced set of phasors VA, VB, and VC. This certainly is a asymmetrical unbalanced set. Now, if you look at this, VA is equal to VA0 plus VA1 plus VA2. This phasor VA0, if we see here, VA0 is having this magnitude and this phase. So, here we have this VA0, then VA1 is, if we go back and see, VA1 is like this. So, again here we have VA1 and similarly VA2, and when we add these 3 phasors, we are getting this phasor VA. Similarly, VB0 plus VB1 plus V B 2 will give us this phasor V B, which is this phasor here. Similarly, V C 0 plus V C 1 plus V C 2 will give me this phasor V C. So, we see by having different magnitudes of these phases and angles of these phases in symmetrical components, when we add them we can generate any unbalanced set of 3 phases. So, in reverse we can say that any unbalanced set of 3 phases can be resolved into these 3 sets of symmetrical components, that is positive sequence component, negative sequence component and 0 sequence components. If we want to write this in mathematical terms, we can write this V A is nothing but V 0 plus V 1 plus V 2. Now, why I am writing here? I am not writing here. If you see, I am not writing A 0, A 1, A 2, because we are assuming that phase A is taken as the reference. So, with respect to phase A, we are writing all the quantities. So, we are no longer writing that A. So, V 0 means basically V A 0, V 1 means V A 1 and V 2 means V A 2. So, here V A is equal to V A 0 plus V A 1 plus V A 2, which we are writing as V 0 plus V 1 plus V 2. V B is equal to V B 0, which is same as V A 0. So, we are writing at V 0 plus V B 1. Now, V B 1, if we look into this set, V B 1 is lagging V A 1 by 240 degrees, right. Now, here we have introduced an operator A, which is basically a unit phasor with an angle of 120 degree in the positive direction. So, when I operate V A 1 with this phasor A, then what I get is this phasor A is now moved to this position, and if I operate it again by A, then it gets moved to this position. So, basically V B 1 is nothing but A square V A 1. So, if we see from that point of view, then we have V B 1 is same as A square V A 1. Since we have taken A as reference and we are not writing A for this, so we are writing this as A square V A 1. Similarly, plus V B 2. V B 2, if you see here, this is V A 2, and if we multiply it by phasor or operate the operator A on this, then this gets displaced to this position. Therefore, V B 2 is nothing but A times V A 2. So, we are writing here as V B 2 as A times V A 2, since we are using A as reference. So, it is A V 2. Similarly, V C is nothing but V C 0, which is same as V A 0, plus V C 1, which is again A times V 1 V A 1 or V 1, plus A square V A 2, which is basically V C 2. So, V C 2 is A square V A 2 or A square V 2. Here, as I said earlier, we are defining this operator A as having a magnitude of unity and a phase angle of 120 degree, which in rectangular coordinate version you can write as 0.5 plus j root 3 by 2 or plus j 0.866. So, this is the operator A, which is allowing us to write for all other symmetrical components in terms of symmetrical component phase A. So, if we have V A 1, then we also know V B1 and we know VC1, because VB1 will be A square VA1 and VC1 will be A VA1. So, similarly for the negative sequence components and 0 sequence components, because of the symmetry, from the 9 unknown quantities we have basically brought it down to again 3 quantities only. That is, we need to know only VA1, VA0 and VA2. If we know these, then VB0, VB1 and VB2 is known, VC0, VC1 and VC2 are also known. So, writing this set of equations where we write A, B, C quantities as phase quantities. So, we write this as Vp is equal to again a set of phase voltages Va, Vb and Vc is equal to this matrix, which is 1 1 1 for this 1 V0 plus 1 V1 plus 1 V2. So, 1 V0 plus V1 plus V2. Vb is equal to V0 plus A square V1. So, V0 plus A square V1 plus A V2, and Vc is equal to V0 plus A V1 plus A square V2. So, this is what we write in matrix notation, where we write this 3 by 3 matrix, which is a symmetrical component transformation matrix, as a matrix A. So, we write this expression in short form as Vp is equal to A into Vs, where this matrix A is symmetrical component matrix given by this 1 1 1 1 A square A 1 A square, and Vs is the symmetrical component voltage in this case. So, V0, V1, V2. So, vector of symmetrical component voltages. Now, from this relationship, if we pre-multiply both sides by A inverse, then we will get Vs is equal to A inverse Vp. So, Vs is equal to A inverse Vp, and if we take the inverse of this matrix, we will get A inverse is equal to 1 by 3 into 1 1 1 1 A square 1 A square A. This matrix is nothing but basically the transpose of this matrix, but 1 by 3 is coming here. So, it is multiplied by 1 by 3 with this, and this is the relationship that we get. A inverse is 1 by 3 1 1 1 1 A square 1 A square A. So, since we know A and A inverse, we can always convert the phase quantities to symmetrical component quantities and vice versa. So, we can write V0, V1, V2, that is the symmetrical component quantities in terms of phase quantities VA, VB, VC. This will be the A inverse matrix that we have 1 by 3 into this. So, we get, if we expand this, we can write this as V0 is equal to 1 by 3 VA plus VB plus VC, and V1 is equal to 1 by 3 VA plus A VB plus A square VC, and V2 is equal to 1 by 3 VA plus A square VB plus A VC. So, this is the relationship between the sequence quantities and in terms of the phase quantities. Same relationships can be obtained for the currents, just like we obtained for the voltage. So, here if you look at this, we write IP is equal to AIS, which can be written as IA is equal to I0 plus I1 plus I2, IB is equal to I0 plus A square I1 plus AI2, IC is equal to I0 plus AI1 plus A square I2. Again here the phase, since we are not writing A, because A is the reference phase, and same thing if we want to write the symmetrical component currents in terms of phase currents, we will write I s is equal to A inverse I p, which in expanded form can again be written as I 0 is equal to 1 by 3 I a plus I b plus I c, I 1 is equal to 1 by 3 I a plus A I b plus A square I c, and I 2 is equal to 1 by 3 I a plus A square I b plus A I c. So, this is what we do, that is, we have the voltage and current transformation from phase quantities to symmetrical component or from symmetrical component to phase quantities using A and A inverse matrices. Now, we will talk about how to compute power in terms of sequence quantities. So, power in sequence networks can be written. Now, 3 phase power can be written as V A into I a conjugate, where we are writing this V A in terms of voltage from phasor A to ground or neutral, that is phase voltage. So, V A g into I a plus V B g into I b, this is I b conjugate, because we have seen earlier that P plus J Q is given by V I conjugate. So, we are writing this complex power as 3 phase power as the sum of the power in each of the 3 phases A, B and C. So, A phase power is V A g into I a conjugate, B phase power is V B g into I b conjugate, and C phase power is V C g into I c conjugate. This in matrix form can be written as S 3 phase is equal to, this is row vector V A g, V B g, V C g, and this is a column vector I a conjugate, I b conjugate, I c conjugate. This, if we write this also as a column vector, which is the normal way of writing the vectors, then we can write this V p transpose, because V p, if you remember, we had written this as a column vector V a, V b, V c. So, V p is like this, therefore, we are writing this as V p transpose into I p conjugate. Now, if we see that, then in terms of, if we write this in terms of symmetrical component, then V p is equal to A into V s. So, it is A into V s transpose, and I p is A into I s. So, it is A into I s conjugate. Now, if we do this, then if we take the conjugate of this, then we will get this as this. If we take the transpose, then this is V s transpose A transpose. So, V s transpose A transpose into A conjugate I s conjugate. So, we have done this A transpose A conjugate together. So, if we write that A transpose A conjugate, then we will get this A transpose as this 1 1 1 1 A square A 1 A square, and the conjugate of A is, this is A and its conjugate. So, if we do this conjugate, then what happens is A becomes A square and A square becomes A. So, here when we do that and then multiply, then we will find that this comes out to be a diagonal matrix with 3 in the diagonal terms, or this can be written as 3 multiplied by unity matrix, that is A transpose A conjugate is 3 times unity matrix, 3 into unity matrix. So, if we substitute that, then we get 3 phase complex power as 3 times V s transpose into I s conjugate. So, if we write here again this, then this is V s transpose and I s conjugate. I am sorry, here 3 is missing. So, this should be 3 times this V s transpose and this is I s conjugate, and therefore, this is 3 phase power is equal to 3 times V 0 I 0 conjugate plus 3 times V 1 I 1 conjugate plus 3 times V 2 I 2 conjugates. This is nothing but the total power in the complex power in the sequence networks or in the sequence components, 0 sequence component, positive sequence components and the negative sequence component. That is, since we have 3 phases there, so the total power will be sum of the 3, and since they are symmetrical, so the power in 1, that is in A, will be same as in B and C. So, that is why it is multiplied by 3 here. So, 3 phase power is given by this, which is nothing but the sum of the symmetrical component powers, which tells us one very important property of symmetrical component, that this component transformation, symmetrical component transformation, is power invariant. So, power in phase quantities and power in sequence component quantities are same. Now, let us go into trying to find out the sequence component model for 3 phase loads. We will start first with a balanced star connected load, which is having its neutral grounded. So, here we have an impedance load, which is a balanced star grounded load. So, this is a balanced star connected load Z y, Z y and Z y in the 3 phases, and the ground or the neutral is connected to ground through an impedance Z n. The currents flowing in this load are I A, I B in phase B and I C in phase C. The voltage with respect to ground for phase A is V A G, for phase B is V B G, and phase C it is V C G. So, this is the system that we have, and this is a balanced 3 phase star connected load with neutral grounded. We want to find out its sequence component network, or when we transform this in terms of the symmetrical components, what is the kind of network that we are going to get. So, let us see how we do that. If we write the voltage relationship VAG, VAG, what is this voltage? This voltage is going to be equal to IA into ZY, this drop which is taking place, plus IN into Zn. So, from here if we see, this IN into Zn is the voltage rise here, and IA into Zy is the voltage rise here. So, from here to here the voltage VAG is nothing but sum of these 2 voltage rises or the voltage drop if we are seeing the current flowing from phase A. So, the same thing that we have written here, VAG is Zy into IA plus Zn into IN. Now, what is this current? IN. If IA is flowing like this, IB is flowing like this, and IC is flowing like this, then IN is nothing but sum of these 3 currents, IA plus IB plus IC. So, IN is IA plus IB plus IC. So, that is what we are writing here, Zn into IA plus IB plus IC. Now, if we arrange this in such a way that currents IA, IB, IC are separated, then we have Zy plus Zn into IA plus Zn into IB plus Zn into IC. In the same way, we can find out the voltages for phase B and C. VBG will be equal to Zn into IA plus Zy plus Zn into IB plus Zn into IC, and VCG will be Zn into IA plus Zn into IB plus Zy plus Zn into IC. In matrix form, we can write this as VAG is equal to Zy plus Zn into IA plus Zn into IB plus Zn into IC. In same way for VBG and VCG. So, we have VBG is equal to Zn into IA plus Zy plus Zn into IB plus Zn into IC, and VCG is Zn into IA plus Zn into IB plus Zy plus Zn into IC. Now, this in short form we can write as Vp is equal to Zp into Ip. where this 3 by 3 matrix we are writing as ZP. Now, we multiply both sides with A, or we convert these phasor quantities in terms, or write these phasor quantities in terms of symmetrical component quantities, then Vp can be written as AVS and Ip can be written as AIS. So, AVS is equal to Zp into AIS. Now, from here if we pre-multiply both sides by A inverse, then we have here A inverse A will become unity matrix. So, we have Vs is equal to A inverse, will pre-multiplying this side. So, A inverse Zp into A into Is. This we can write as Vs is equal to Zs into Is, and what is this Zs? This Zs is nothing but A inverse Zp into A. So, the symmetrical component form positive, negative and 0 sequence impedances of from the phasor quantities can be found using this relationship. Zs is equal to A inverse Zp into A. So, now if we do this multiplication, then we have Zs is equal to A inverse is 1 by 3, this matrix 1 1 1 1 A square 1 A square A. This is Zp matrix that we had, Zy plus Zn, 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 Zy plus Zn, Zn and Zn, Zn, Zy plus Zn. So, Zy plus Zn in the diagonal elements and Zn at the off diagonal elements. So, this is A inverse Zp into A. So, A is this matrix. When we do this multiplication, we will get this as Zy plus 3 Zn 0 0 0 Zy 0 0 0 Zy. What we find is we have got a diagonal matrix where the first element, which is corresponding to the 0 sequence terms, is Zy plus 3 Zn, whereas the positive and negative sequence quantities are Zy and Zy. Now, what is the difference that we have found here from the phasor quantities and in the sequence quantities? If you see here, Zp is a 3 by 3 matrix with all off diagonal elements present, whereas this Zs is a diagonal element, no off diagonal terms. What does it mean? The 3 sequence networks are uncoupled with each other. There is no coupling between the network, whereas here phase A and B has a coupling of Zn, phase A and C has a coupling of Zn, that is ZAC is equal to Zn, ZAB is equal to Zn, same way for other terms, whereas here there is no coupling, there is no terms as Z10 or Z02 or Z12, those kind of terms are not coming there at all. That is, for a balanced 3 phase network that we have is now transformed into 3 independent sets of network, which is much simpler. So, if we are putting this voltage relationship, then we have this Vs, which is V0, V1, V2 is equal to this Zs, which is a diagonal matrix, into Is, which is I0, I1, I2. So, what we see is we have 3 independent equations. V0 is equal to Zy plus 3 Zn I0, which we can write as Z0 I0. V1 is equal to Zy into I1, which we can write as Z1 I1, and V2 is equal to Zy into I2, this is equal to Z2 into I2. So, we have 3 equations which are independent of each other, they are not coupled equations, which is the case when we work with the phasor quantities. So, if we see in terms of the network, then we have the 0 sequence network like this, which is Zy plus 3 Zn, V0 is the voltage applied to this and I0 is the current flowing in this. Now, in case of this network, we are finding that Z0 is equal to z y plus 3 z n. Now, if the neutral in this was not grounded, then what would have happened? This z n, since this is an open circuit, this z n would be infinity, which is same as saying that this will be open. So, what does it tell us? This will be open in case the neutral point is not grounded. So, in case of circuits where we do not have a ground return available, then this zero sequence network will be open, means no zero sequence current can flow. This is a very, very important relationship that we obtain. So, for star ungrounded load, Z n is infinity and zero sequence network is open. So, no zero sequence current can flow. Similarly, positive sequence network we find is same as Z y, and negative sequence network is impedance is same as Z y, voltage is V 2 and current is I 2. So, this is how we get three separate networks for a balanced three phase load system. Now, if we have a balanced delta connected load, what will happen? Well, it is very easy to analyze this, because we can always convert the balanced three phase delta load into an equivalent balanced three phase star connected load, where if we have the Z delta as the impedance value of the delta branches, then the equivalent star branch impedance will be Z delta by 3. So, this will be Z delta by 3, this will be Z delta by 3 and this will be Z delta by 3. This is the equivalent star for this balanced delta network. Now, if we see this again, what we find that Z 0 will be equal to Z delta by 3 and Z n, since there is no Z n connected, because this is neutral ungrounded. So, this is open, that means Z 0, which is this Z delta by 3 plus Z n, since Z n is infinity. So, Z 0 is infinity, this is an open circuit, that is in case of delta connected load there will be no zero sequence current flowing in the lines. Similarly, positive sequence and negative sequence network for this can be obtained, where positive sequence impedance will be Z delta by 3 and negative sequence impedance will be Z delta by 3. The currents in them will be positive sequence current, voltage will be positive sequence voltage across the terminals. These three networks again are independent from each other. Now, let us take the case of a general three phase impedance load, means a load which is not a balanced load. It can be a star connected load, a delta connected load, ungrounded or grounded, whatever it is. We can write down the relationship for this general situation. The currents are I A, I B and I C. The voltages are V A G, V B G and V C G between the phase and the ground, and the current in the ground will be this neutral current or I G flowing. Now, we have for this system the phase values as Z A A, Z A B, Z A C, that is the mutual terms Z A B between A and B and A and C will be there. Similarly, this will be Z A B, this is Z B B, Z A A, Z B B and Z C C are basically the self impedance of these three branches, and A B, B C and C A are basically the mutual impedances which are involved. So, again we can write Z s is equal to A inverse Z P into A. So, Z s is nothing but Z 0, Z 0 1, Z 0 2. These are the mutual terms which we are writing for 0 sequence to positive sequence, 0 sequence to negative sequence. Similarly, positive sequence to 0 sequence, positive sequence and positive sequence to negative sequence. So, we are writing the 9 terms for the 3 by 3 matrix, including the coupling terms between the sequence networks. So, if we do this A inverse Z P A, then we have 1 by 3 this matrix which represents A inverse, this is Z P and this is A, and if we do this all multiplication, then we get Z0 is equal to 1 by 3 ZAA plus ZBB plus ZCC plus 2 ZAB plus 2 ZAC plus 2 ZBC. Z1 will be equal to Z2 will be equal to 1 by 3 ZAA plus ZBB plus ZCC minus ZAB minus ZAC minus ZBC. Z01 will be equal to Z20, and this will be equal to 1 by 3 ZAA plus A square ZBB plus AZCC minus AZAB minus A square ZAC minus ZBC, and Z02 is equal to Z10 will be equal to 1 by 3 ZAA plus ZBB plus A square ZCC plus minus A square ZAB minus AZC minus ZBC, and Z12 similarly will be equal to 1 by 3 ZAA plus A square ZBB plus AZCC plus twice AZAB plus twice A square ZAC plus twice ZBC, and Z21 is equal to 1 by 3 ZAA plus AZBB plus A square ZCC plus twice A square ZAB plus twice AZAC plus twice ZBC. Now, if we see in this case all the 9 terms, that is the coupling terms between positive and 0 sequence and negative sequence, will be present for a general 3-phase case. That is, for an unbalanced 3-phase load, there is going to be coupling between the 3 sequence networks. If we put ZAA is equal to ZBB is equal to ZCC, that means the self impedances are same, and similarly the mutual impedances ZAB is equal to ZAC is equal to ZBC, then this is what we get will be a symmetrical 3-phase load, and in that case we will find that Z01, Z10, Z02, Z20, Z12, Z21 all become 0. That is, all off diagonal terms become 0, and Z0 becomes ZAA plus twice ZAB, and Z1 is equal to Z2 is equal to ZAA minus ZAB. So, this is what happens in case we have the symmetrical network, then the 3 networks become uncoupled. If the network is unbalanced, then there is this decoupling does not take place and mutual terms will be available, which means that the 3 sequence networks will be connected with each other. There are going to be mutual terms between them. Since most of the network elements are designed to be symmetrical network, therefore, we are going to get 3 uncoupled networks. Now, let us take a simple example to illustrate this point. We have, for example, we have taken a 3 identical star connected resistors from a load bank with 3-phase rating of 2300 volt and 500 kVA. I am sorry, this is form, not from. 3 identical star connected resistor form a load bank, means we have a star connected load with 3 resistors of equal resistance. The rating of the 3-phase load, the voltage rating is 2300 volt and the kVA base is taken as 500 kVA. If each bank has applied voltages of VAB is equal to 1800 volts, VBC is equal to 2700 volt and VCA is equal to 2300 volt. That is, the applied voltage is asymmetrical or unbalanced. The load itself is a balanced impedance. Now, since we have seen that for balanced impedance load, we get the 3 sequence network which are uncoupled. So, here even though the voltage applied is unbalanced, we will get an uncoupled network for the 3 sequence. Find the line voltages and currents in per unit into the load. Assume that the neutral of the load is not connected to the neutral of the system and select a base of 2300 volt 100 kVA. So, this is what we have, that is, we are using a base of 2300 volt 100 kVA, whereas the load values are given on a 500 kVA base and 2300 volts. So, voltage base is same as what we have chosen, but the kVA base for the load is 500 kVA, whereas our chosen base is 100 kVA. We could have chosen 500 as well, but this is just to illustrate how we can have different bases and we can convert them to per unit quantity for any given base MVA or voltage level. Okay, now we would like to solve this. So, on 2300 volt 100 kVA base, line voltages in per units are VAB is given as 1800. So, 1800 by 2300 comes out to 0.7826. VBC is given, magnitude is given as 2700. So, 2700 by 2300 is 1.174. VCA is equal to 2300. So, it is 2300 by 2300, which is 1 per unit. Now, let us choose one base that we can use as a reference is one of the voltages, we can choose its angle as a reference, the others will come out with respect to that. So, let us take the reference of voltage VCA with 180 degree to be taken as a reference value. Then we will get VAB is equal to 0.7826 angle 81.39 and VBC is equal to 1.174 angle minus 41.23. Now, symmetrical components of the line voltages will be, if we write this, VAB1 will be equal to 1 by 3 VAB plus A VBC plus A square VCA. This is the same relationship that we have written earlier. So, now substituting the values, we will get VAB1 is equal to, finally putting all these values and solving, as 0.97236 angle 73.147 degrees. So, we know the values of VAB, VBC and VCA, and A square are known. So, substituting that, here A is equal to 1 angle 120, A square is 1 angle 240. So, this is what we have done. So, and then adding them together by converting them to rectangular coordinates, we get this result for VAB1. Similarly, we can write VAB2 in the same way as 1 by 3 VAB plus A square VBC plus A VCA, and then substituting the values, we will get this as equal to 0.2272 angle 223.627 degrees. Now, similarly, we will get VAB 0 as 1 by 3 VAB plus VBC plus VCA. If we do that, we find that this comes out to be 0. This one need not compute because the neutral is ungrounded. So, we know that VAB 0 is going to be 0 because there is no 0 sequence current which can flow. So, instead of the line voltages, if we want, we can calculate the voltages to the neutral. So, VAN 1 is equal to the same value we are writing, because we are taking it on a line to neutral base. If we take it on a line to line base, then we will have to divide it by root 3. Now, here what we see is VAB 1 whatever is there. If we look at this diagram, VAB is in this direction, VAN is in this direction, that is VAN is lagging VAB by 30 degrees. So, this is VAB which we had, and we have subtracted 30 degree from that. So, we get VAN. If we are writing it on a line to line base, then we will have to divide it by root 3. So, otherwise if we are taking it on a line to neutral base, then this remains same. So, 0.97236 with an angle of 43.147. Same thing for the negative sequence, we will find that VAB2 was this value, and because the sequence is rotation is in the reverse direction. So, instead of subtracting that 30 degree, in this case VAN2 will be leading VAB2 by 30 degrees. So, we have added this 30 degree. So, this gives us this value on a line to neutral base. Resistance value in per unit can be calculated, since we have been given at 500 and we have to calculate it on 100. So, it comes out to be 0.2 per unit, and therefore, we can calculate IA1, which will be nothing but VA1 divided by the resistance or the impedance. So, VA1 by this resistance or impedance. So, this comes out to 4.8618 angle 43.170 per unit. Similarly, IA2 is nothing but VA2 divided by the resistance, that is 0.2. So, this comes out to 1.136 angle 253.627 per unit, and IA0 is going to be 0, because there is no neutral connection in this case. So, this is all we are going to do in today's lesson. In the next lesson, we will talk about how to find out the sequence network for other components such as transmission lines, transformers, generators, and how to build sequence network for a given power system. So, with this we end today. Thank you very much.